Okay, suppose we have this function as shown here, polynomial function, and what we can see is that everywhere the function is red, it's increasing in value, and then when it starts to decrease in value, it turns blue, red it's increasing, blue decreasing, red increasing. All right, so let's take a look at the tangent here, and what we can see is that whenever the slope, whenever the value of the function is increasing, the slope is positive. But as soon as it hits here, the slope goes to 0 and then becomes negative for this entire portion of the function. And so what we're doing when we're plotting the first derivative is we're just plotting a set of points, the x values of which will be the same as the x values of the original function, but the y values will just be the slope of the function at that point. So right here, what we would expect is that if we look at this x value, which is a little less than 7, when we look at the x value on the first derivative, we would expect that that would have a value equal to 0. All right, so let's look at the first derivative. And as we can see right here, where the same x value as this point s, we see that our first derivative has a value of 0. And what that means is that the slope of the function at that point is equal to 0. Notice now as well that everywhere that our function is red, which means increasing, our slope is positive, and that means our first derivative is positive. So when we look just at our first derivative here, we can see that red, the function's increasing, blue it's decreasing. Red it's increasing, blue it's decreasing. So whenever our first derivative is positive, it means the slope of the original function is positive, which means that the function is increasing at those points. Whenever our first derivative is negative, as we can see wherever it's blue, it means that our function is decreasing, and therefore it has a negative slope, which is why our first derivative is negative. Notice then, whenever we see these peak values or these lowest values at Q, at R, at S, at T, those represent points where the slope is changing from positive to negative or negative to positive, which means that we have achieved either a local maximum or a local minimum. And those show up in our first derivative as places where the first derivative goes from a positive to a negative value, as is the case right here, or from a negative to a positive value. So these x-intercepts of the first derivative correspond to our local maximum and local minimum points. Okay, so the other thing we can look at is what happens if we look not at where our function is increasing, but where it's concave up and where it's concave down. So you'll notice now wherever it's concave down, it's marked as red. Concave up, it's marked as blue. So whenever we have, if we look back here, we can see that our slope right now is 8.264, and our slope is decreasing, and that's what happens when you're concave down. Decreasing, decreasing until it reaches a 0, but then it keeps decreasing and it becomes negative and keeps getting to be a lower negative value until it reaches this point n, and it's reached its lowest value the slope has of negative 1.292, and now it's starting to come back up again. It's still negative, but it's no longer decreasing, it's increasing. And it keeps increasing, gets to 0, and then goes positive, and keeps increasing until it reaches this point. And then at that time, it has reached its maximum slope here at 7.773, and now our slope is decreasing, decreasing, decreasing all through this concave down portion until it reaches this next point, P. These points where it changes from the slope increasing to decreasing or vice versa are inflection points. Now, when we look at our first derivatives, those inflection points show up as minimum, local minimum points or local maximum points on the first derivative. And that makes sense because as long as our slope is increasing, then, or decreasing, I should say, over this red portion, then our slope is decreasing, which means the first derivative is decreasing. It keeps decreasing until it reaches this point here where it starts increasing. So on our first derivative, these inflection points show up as local maximum or local minimum points. Okay, so notice that over the red portion of the original function here, where the slope is always decreasing. When we look at the first derivative over that time, part of it is positive, part of it's negative, and that's because the slope started at a positive value, kept decreasing till it reached 0, decreasing, 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 until it reached this lowest value, then it started increasing. So whether our first derivative is positive or negative doesn't tell us anything about the concavity of the original function. What does tell us something about it is whether our first derivative is decreasing, which means concave down, or increasing, which means concave up. Okay, now when we look at our second derivative, we get more direct information about the concavity of our original function. So what we can see here is that when our function is concave down, our second derivative is negative. When our function is concave up, our second derivative is positive. Concave down, second derivative negative. Concave up, second derivative positive. That makes sense because really the second derivative is just the derivative of the first derivative. So when the first derivative is decreasing, as is the case here, then its slope is negative, which means that our second derivative is going to be negative. And so whenever our first derivative is decreasing, our second derivative is negative. Whenever our first derivative is decreasing, it means that our original function is concave down. Okay, so understanding the relationship between the increasing or decreasing intervals of the original function, which again will show up with our first interval as either positive or negative. Then, so we can look very quickly at our first derivative and see where our function is increasing, decreasing, increasing, decreasing. And what it means for our first derivative is that where it's positive, all the red portions, our function is increasing. Now when we look instead at concavity, we can see whenever the slope is decreasing, it's concave down. Whenever the slope is increasing, it's concave up. The way that shows up in the first derivative is that the first derivative is decreasing. That means the slope is decreasing while the original function is concave down. Our slope is increasing while the original function is concave up. Second derivative shows that it's negative when our function is concave down, positive when our function is concave up. Our second derivative is negative when our first derivative is decreasing, and positive when our first derivative is increasing. And again, this now tells us about the concavity of the function, not about whether the function is increasing or decreasing.